So, good afternoon, everyone. My name is Marco Bittencourt. I'm a professor here at the School of Mechanical Engineering at UNICA. And together with my colleagues, Professor Josué Labach of Mechanical Engineering and Professor Luis Vieira of the School of Civil Engineering, we are organizing the next edition of Mecsol in next October here at UNICA. So we decided to organize this webinar series to promote the conference. Mecsol is a conference organized by the Brazilian Society of Mechanical Engineering every 2 years. And the next edition will be the 8th edition of this conference. So today, it's our pleasure to have here Professor Carlos Manuel Thiago Tavares Fernandes of the University of Lisbon. And today, he will present a talk about glass fiber reinforced polymers profiles subject to fire. And Professor Carlos Fernandes, he's from the University of Lisbon, and he got his PhD in 2007, working on meshless methods applied to geometrically exact structural analysis. And his thesis received in 2008. It was considered the best thesis in applied and computational mechanics by the Portuguese Association of Theoretical, Applied, and Computational Mechanics. His main research interests are related to nonlinear finite element methods, finite rotations, geometrically exact structural analysis of beams and shells, hybrid discontinuous Galecki methods, and mesh-free approximations, plate shells, and the construction of C1 continuous finite elements. He has many collaborations with projects in Europe, and as I told, he's a professor at the Department of Civil Engineering of the University of Lisbon. So, Carlos, it's our pleasure to have you here. Thank you very much for accepting our invitation. And now it's your time. Okay, thank you very much.
Well, first of all, I would like to thank you, Professor Marco Bittencourt, for inviting me. It is a pleasure to be here to present this talk. The good thing that this pandemic teaches is how to use these resources to communicate at distance. So it is a truly pleasure to give this talk to the Mecsol webinar series. I have a long relation of collaborations with Brazil. I must say, I talked about my PhD thesis, so I must say that I spent part of my PhD thesis in Brazil. Not at Campinas, but at USP. So it's a long relation that I have with Brazil. In fact, this work that I will be presenting is also made by Bruno Aguirre, which is a PhD student, which is almost finishing his thesis, and is also from Brazil, as well as Professor Laurent Stanier from École Centrale Nantes, and my colleague in Lisbon, Professor João Correia, okay, which is the main responsible for the part involving the experimental work that I will be presenting. Okay, this will be the contents of my talk. So I will do a brief motivation for using glass fiber reinforced polymers Then I will present a modeling strategy. Then I will specify a bit the thermal model, the structural model, and then I will do a preliminary application of a profile. So in this figure, we can see a conventional pultruded profile. So pultrusion is the way that these profiles are made. In fact, I will show an image in a while about it. So they are FRPs are wide class composite materials consisting mainly two parts: polymeric matrix reinforced with fibers. So this way, these FRPs are in general very orthotropic materials. So they are applied in a wide range. They have a wide range of applications from aerospace, naval, automation, structural engineering problems. So here we can see some facilities on production and also an example of application over a bridge. So applications in civil engineering are more recent, and they have a narrow way of applying them. So they are not. Civil engineering is a field which is very conservative. So mainly it's always the steel structures and the reinforced concrete. So composites are more difficult to apply than the other more traditional materials, and we will see in brief why. So this is some examples of applications of bridges, like this bridge in Switzerland, bridge in Spain, a building in Switzerland. So these are all made of FRPs. Okay. As I told, so this particular FRP, GFRP, is made of polymeric matrix and fiberglass fibers. Then the process to produce them is called the pultrusion. So what are the advantages and disadvantages of this kind of beam? So they are very light, they have a high strength and high durability. Well, the durability, it's more on interior applications. In the exterior, they can also suffer a bit in a large period of time. Okay, mainly due to the ultraviolet rays. So, what are the disadvantages? The initial and production costs, their high deformability, the lack of standards and codes, which is very well established for other materials, their brittle failure, and the fire behavior. I will detail here this last aspect. The fire behavior will be the main focus of this talk. Okay. So, what happens when we expose a profile made of GFRP to fires? Well, they have a poor fire performance. Why? So when they are exposed to high temperatures, the matrix softens and decompose rapidly, compromising the structural integrity. Although the fibers can still stand, but they don't have a way to transmit the load that they can absorb. So it's our objective is the development and the implementation of a model capable of predicting the thermal and the structural response of GFR profile subjected to fire. Moreover, we also want to propose, it is our aim to propose guidelines to designers and, if possible, guidelines to future standard and codes, because they are right now under development here in Europe. So, in order to achieve a successful model, it's necessary to resource the experimental laboratorial tests and also collaboration with industry manufacturers. In fact, the project which this work was developed, it includes a manufacture of GFRP profiles. It's called Auto Perfis Culturados, and I myself visited this factory, and we were able to see how the profiles are produced and so on, to have more insight into the material that we are trying to simulate. So in here we can see the fibers ready to go into the production line. Actually, the production line is quite simple. It's very simple. It's only the machine that we see on the left side, and the fibers enter in one side together with the matrix, and on the other end we have the ready profile. So actually the process of producing this kind of profiles is relatively simple, although expensive. So the experimental setup that we want to simulate, it's this one. Okay, so basically we have a GFRP beam over here in the center, and we have a way of applying loads. It's a 4-point concentrated 4-point bending test. So with 4 concentrating loads, 2 reactions and two loads, and how we want to apply the loading that we will apply consists of 2 constant vertical loads, which are made constant over time, and then we have the application of temperature underneath the beam. So in the furnace we use the ISO 834, which is a standard heating curve. Okay, and this is our setup for the experimental program, which we try to simulate also with the numerics. So here we can see the real setup, the real oven. So this is open air, because the dimensions are relatively big, and for safety reasons these kind of tests have to be made on the outside. Okay, they also resource gas to inject this is the fuel that we inject inside the oven. So I will play a small video which shows us how this takes place. I will reduce the sound because the video has some sound. So the beam of GFRP is this one. In this case, it's a square section. Okay, a square with a single cell. Okay, so here we see that after 20 minutes it all starts to burn, and then this is the failure. Okay, so these kind of tests were made some time ago. Presently, we don't do this kind of test anymore because we found some, or we don't do it exactly like this because we found some limitations. So the first limitation is that we want to emulate a beam inside a building, and the open air convection, we realize that changed a bit the thermal exposing. Also here we see this open cell allows a flux of air along the longitudinal directions, which we know that inside the building it will be very reduced. So Now the apparatus is slightly different from this one that we used at that time. So this is a more recent test, and we put this kind of protection around the beam. Here we can see all these wires. It's merely to measure the thermocouples, the temperature of the thermocouples. Okay, and here is it is showed how the temperature, how the beam in the end of the experiment, top of the beam. So, in order to achieve a trustworthy structural model, the temperature distribution has to be correctly represented. So, the optimal cross-section design of such panels many times includes cells. So, here we see a single cell on the left, which was the one which was tested in the experiment that I showed, and the one on the right is a different one, is a Fiberline 300. So, which has 3 cells. So the temperature distribution will strongly depend on the air convection inside the cells that we see in here. Moreover, there are other phenomena like internal radiation that cannot be disregarded. Okay, so for the time-dependent thermal model, we have several ingredients. So heat conduction, a carrying equation in the beam, which is a Arrhenius-like equation. We have Navier-Stokes with Boussinesq approximation in the enclosed cells, internal radiation between the walls, and of course, external radiation on top and bottom. So we have these main variables. So temperature, decomposition degree, velocity, pressure, and radiosity in between the walls. Well, as for the mechanical part, we have to use for sure large strains, temperature-dependent materials, and full 3D constitutive models, including anisotropy and viscosity. The main variables here, of course, the usual displacements. So why not to use a full 3D simulation for the whole beam? So this, first of all, this is not practical for the engineering which is designing beams. So each beam has to do a full 3D model with computational fluid dynamics and temperature evaluation. So it's too much. And then the computational cost, it's very high. So just for example, I'm giving here some meshes. So on the left, on top left, the mesh of the mechanical part, on the right, the fluid mesh, and then the combined mesh. So this would be, so remember, this is a nonlinear problem at each time step, which has to be simulated for at least half an hour, 1 hour. So it's the computational cost of such analysis would be too much, okay? Moreover, there are other disadvantages related in here. For instance, if we use a 3D simulation, we get stresses and strains. So in general, in civil engineering, we prefer to work with moments, generalized quantities, generalized stresses like moments and forces. So there are several disadvantages associated with a full 3D simulation. So what is the alternative that we thought? Well, why not a 2D thermal analysis in cross-section, assuming that there's no significant variation of the thermal quantities along the axis of the beam, plus a shell model for the mechanical part. So this would at least decouple part of the problem, okay? And of course, we are assuming that changes in geometry don't change significantly the temperature, which is quite reasonable, assumption. So the phenomena involved in a typical cross-section of a typical beam are, so for the simplest cross-section that we can imagine, it's something like this. So we have the furnace here in the bottom, we have the radiant emissivity and heat convection. On top, we have the ambient temperature and external radiation and convection. We assume that we have a diabatic boundary conditions on both sides, which is quite miserable in a construction, and then internally we have the convection and the radiation in between the walls. So this is the phenomena that are decisive here and we have to include. So which equations govern these? So this is like the normal equations that you would expect. So together we have the Navier-Stokes equations over here, including, of course, the Boussinesq assumptions. Then we have conservation of energy, and then we have the relation of, well, constitutive relations for the heat, and then we have the boundary conditions, convection, radiation, and the radiation in between the walls. So there is here a variable called radiosity, which is a kind of flux in the walls. Okay, so these are the main ingredients in terms of the equations that we need to solve. So here they are all gathered, okay, for a general situation. Okay, so this is the complete problem. Well, here I'm not including the Arrhenius equation, which sometimes we use and sometimes we don't use and put exactly the thermophysical properties at once. So these are the standard weak forms of each of the governing equations. Okay, I'm not going very much into the details in here. So we have the weak forms, we have their discretization. Okay, so we have on one side 2D for the temperature, for the fluid velocity, for the pressure, and on the other side we have 1D elements along the internal cells for the radiosity. We use here very standard Lagrangian elements. Okay, so it's quite standard finite element apparatus. So for time, we use the generalized ellipsoidal family of methods. In general, we use implicit and with a given time step, which we can tune along the analysis. So in the end, we have this elementary residual, which is solved by within a Newton-Raphson iteration. Okay, here the matrices are non-symmetric due to the presence of the radiosity. So this is quite standard finite element calculations. Well, just a couple of examples. So this is that main square with a single cell cross section. So in the bottom I will show the temperature, and in the top I will show the velocity. So the temperature, we have temperature in the profile, which is the part that we are interested with, and we have the temperature in the fluid. So this appearance of these Bénard cells, it's very typical of this kind of behavior. Okay, so of course we control the Rayleigh number in order to be sure that we don't have here turbulence involved. Attention that the time scale here, this is going very fast, because what I'm showing is I think it's about 1 hour of simulation, and here we are going too fast. So in reality, this is not as fast. So you can see here the temperature evolving, okay, and so the air, the hot air is coming from the bottom flange to the top flange, okay. I will speed up this a bit. Okay, and so this is in the end of the simulation. So, and then in the end, we pick up all these values and we will change them, and we will transform them into the mechanical value. Some notes on discretization. So here we are using those standard quadratic 2D triangular elements for temperature and velocity, the 3-node linear for 2D triangular elements for pressure, and 3-node also for the radiosity variable. So, what about the more complicated cross-section? Well, in a more complicated cross-section, we have to be careful with the discretization because of the boundary layer created by the fluid, but this is a typical mesh that we will use. And here I will show some snapshots of the simulation. So here we entered with the decomposition degree. So in this top figure, we will see the temperatures, and in the bottom figure, the decomposition degree in the solid, and also the velocity field in the cells. Okay, this is 120 seconds at this point. So, and we see the cells, the convection cells are starting to form. In the beginning, this is quite symmetric, but then it loses the symmetry, and we see the evolution of the temperatures in the bottom flange. Okay, in fact, here is the composition degree, which varies from 0 to 1. The temperature is on top. So we see the evolution of the temperature, formation of the cells, temperature getting to the webs, and that's it. So this is just some results on this cross section. So as for the structural model, so now that we have a temperature distribution and we know the temperature distribution along the time, how to incorporate this information in a mechanical model? So what are the requirements that we can use? Well, for convenience, we would like to use full 3D constitutive relations, because our collaborator in SEN has a material library which is very tested. We don't have to develop it from the scratch, and it incorporates all the materials that we need. It is quite general, and of course, use of shell constitutive equations has some disadvantages. So, if we use shell constitutive equations, we would have to introduce like a plane stress assumptions, but as we are using a large strain and large displacement theory, well, this plane stress assumption has to be imposed in the deformed configuration, and well, it's not difficult, but it creates an extra loop, an extra 1D Newton-Raphson loop at each integration of each mid-surface point. In order to avoid this, well, can we do it? Of course, and we can use more general constitutive laws by using a more sophisticated shell theory. Which shell theory? Well, the main ingredient here is to include a description of the thickness variation. Okay, so usually we say, well, the shell has to be rigid. No, the shell doesn't have to be rigid, it can vary. So we just have to introduce the right ingredient to describe the thickness variation. So the main schematic of the shell is an initial configuration. This is a reference configuration. Here is a reference. Here is an initial, and this is the current configuration. Okay, so this initial configuration, we assume that is a kind of Kirchhoff-Love mapping type from the reference 1, okay? And from here to here, it's a kind of, it's a general mapping. Well, the nice ingredient of this theory, okay, it is the possibility of including a thickness variation description. Which description? Well, we include a linear term, which you can see by this degree of freedom, is P, and a quadratic term, which is described by K. The rest, well, the rest is quite standard these days. Well, this kind of geometrical exact theories started in the beginning of the 90s with the CIMO. Well, there was, of course, work before, but not on this level of implementation in combination with finite elements. So this is the description in the reference configuration, which is quite standard. This is description over the initial configuration. Well, key is a rotation tensor, okay, which maps a director from the reference configuration to the initial configuration. And then in the current configuration is described by mid-surface plus a director here, which can stretch. The thing here is that the director itself can stretch in the current configuration. Well, the relation between the initial and the reference configuration is given by effective rotation tensor, which is described by the well-standard, by these days, the Euler-Rodrigues formula. Well, these H's, for instance, are trigonometric functions, which are a function of the rotation, the norm of the rotation vector. And for instance, this theta in here is the skew of the rotation tensor. So the main thing is that this is a rotation tensor that maps initial configuration into the current configuration. Okay, it's just that, and does it exactly. There's no approximations in here. Of course, there are some limitations on the use of this specific parameterization with the so-called vector description of rotations that includes only 3 parameters. So, for instance, at each time step, we cannot have rotations over 2 pi, but that hardly can be achieved, so it's not a practical limitation. So, introducing these kinematic assumptions, what can we expect? Well, we will attain shell theory with 8 degrees of freedom per node. Which degrees of freedom? Well, it's 3 displacements, the parameters of the rotation vector, which I don't like to call it a rotation, and the 2 extra parameters which describe thickness variation. So, some key steps, just for a reminder. So, we will have the internal work described right here. This is the first pure Kirchhoff stress tensor and the variation of the strain gradient. We have some generalized stresses and strains. Just to draw your attention, so here we have forces, well, in plane and out of plane forces, shear forces and axial forces, if you want. Here we have bending and torsion moments, but what are really these quantities here? It's quite simple. So this is by force, by shear, and these are by moments. These are the so-called first order, and these are the ones associated with the second order. Basically, they involve integrals of quantities on psi and psi squared in the cross section. Okay, So the generalized displacement vector is something like this. So P and Q are scalar quantities defined over the mid surface. Well, a word of conscience, of course, if we just use a normal finite element, we will have, there are lots of reasons that we can attain a locked solution in here, okay? So there is the coupling between the bending modes and the shear modes. Between the bending and the membrane modes, we can have the incompressibility limit because we are using a full solidity law. So we have to be careful. Here we opt by using a simple rotation non-conforming variable DOF per node triangular finite element, which is well tested by now. Okay, so the resulting nonlinear system is solved by Newton. We have quadratic convergence. The tangent is symmetric, provided the material tangent is also symmetric, and the loading is conservative. So, what about this the constitutive model? Well, as we can use 3D, well, then we have lots of possibilities. So we used what is that Matlib library that I told you about before. So we use a general thermo-viscoelasticity model described by this rheological model that we can see here. And this is, of course, written in terms of incremental variation framework. So just a very simple overview. Okay, so we have a combination between a free energy potential and a pseudo potential. Well, this is of course a function of the gradient deformation, of the viscous deformation gradients. So we have here several variables to take care. And in the end, the internal variable update over a time step is performed by minimizing this incremental potential. Okay, delta T is represented in here. So, what about the free energy potential? Well, it is quite standard. Well, we introduce here some function of the fibers. Okay, the inclusion of the fibers is essential in both these potentials. Well, let's see some simple examples on what we can have from this theory. So this is a mesh. We will do a very simple cantilever beam, okay, with tip loading. Well, when I say tip loading, I cannot just apply a load in the tip, because if not, we would have a large deformation in there and not a global deformation. So in fact, we apply the load in top of the webs where there is webs and in a little line over there. So this is one of the views of the deformed shape, and the first thing that draws our attention is what's going on in here. Well, it's just a local buckling of the bottom flange of the beam. Okay, so here is three deformed configurations of the beam, and here you can see what are we getting in here. So it's just local buckling. Maybe I forgot to say that we are using here a simple neo-Euclidean material, so hyperelastic constitutive relation. So this is a small illustration of a static analysis. So this is just a sequence of events. This is static, not dynamics. Okay, there's no dynamics in here. It's just sequence of events. Okay, so let's look now at a crucial step, because I have this cross section, this green one, which is a real one, complicated one. I have this mid surface, but how do I transfer information from one into the other? So they are not really the same. We see that there are some differences in between what is a shell and what is the exact cross-section. So we have to devise here an algorithm to transfer the thermal information into the mechanical part, okay? And we see, for instance, this part that it's not overlapping, so it's impossible to transfer this part of the information, okay? But that's the price to pay. This is still a shell, although a sophisticated shell model is still a shell, it's not a 3D. So, to feed this constitutive relation, of course, we need data. And where can we get this data? From the manufacturer or from the lab tests? We did some of the tests right in our lab. This is the work of my colleague João Correia and his group. So here we have, for instance, a traction test on a sample at the ambient temperature, okay? And we see how this behaves in the end. So here is the beginning, here is the final configuration, okay? So this is a traction test, shear tests, okay? And you see how a sample is in the end when subjected to a shear test. We are still doing, we have done one even yesterday, a 4-point bending test. This is just to assess the linear behavior of our true beam, okay? It's a 4-point test. We see here all the instrumentation, so this is a cell load. Here we have a beam, a rigid beam, just to split the load in two. We have here the sensors to capture the displacement. We have more sensors on the supports, but as we can see in here, okay, so these are all sensors to capture both the displacements, and we see here a sensor, a strain gauge to capture, to measure also the deformations in the beam. So this is not a finished work, this is an ongoing work, and we are still trying to assess these properties. This part of the work is significantly delayed by the COVID, although at home we can program and we can get on with the computational part. The experimentals, we still need the lab, and this part was strongly affected by the pandemic. So this is a combined load compression test at elevated temperatures. We see here a compression test, but inside the oven, okay? So this is what we can expect. We have a sample right in the beginning, in the middle, okay? And we measure the stress strain in time in compression, because the behavior in tension in compression is different. So all these tests are made right in our lab, in our department. So as I said, the experimental campaign is still going on. We have our complete model from the computational point of view. Unfortunately, we don't have still the data to feed it. So what we have done, we resort manufacturer data, but the manufacturer only gives data at ambient temperature, and we resource some bibliography to try to start to run some tests. But as I say, this is not still something that we can compare with our experiences. This is an ongoing work. So as closure, we can say that the simulation of fires into these FRP profiles is a challenging multi-physics tasks, because it involves very different kinds of physics. So we try to propose a model which is decoupled, in order just to avoid the full 3D analysis, which would be quite complicated and cannot be done to design a very simple beam, okay? In practice, it cannot be done for each beam, for each span, for each loading. It would be very complicated to do that. So we try to to provide something which is simpler, and I think we can still, there is here room to simplify even our model, and it's also very important in here the experimental part on laboratorial tests. This is a key ingredient, and we are waiting for these results. And well, maybe I can present them on the real Mecsol in October. So I would like to thanks for your attention, and if you have some questions, of course, I will be available.
So Carlos, thank you very much for your very interesting talk. And now we are open for questions. If anyone wants to type any question in the chat window, you can translate it to Carlos. So Labak, please.
Professor Carlos, thank you for your talk today. I have very basic questions just out of curiosity. It's a very complicated problem. And when we design structures, we're usually interested, our failure criteria is that the structure remains in the linear elastic regime, which is kind of a simple requirement when you think about what you're talking here, right? It's a very complicated phenomenon. And now you're saying you found out that when you use FRPs, now the area that's exposed to fire is also very relevant, right? The behavior of the structure is strongly dependent on the area that's exposed to fire.
Yes.
So that adds an additional layer of design. So if you're designing a bridge or a building, now you have to be concerned not only with moment of inertia or the kind of things, but you have to design as well, look at the area that's exposed to fire. I was wondering if you came up with any guidelines for engineering design that consider this. Like if you're designing some kind of structure with this kind of material, this is what you have to take into consideration.
Well, as there is, in fact, well, in the last 3-4 years, it's under development. A standard code here in Europe for FRPs. There are already things in United States and I think Australia, but there's nothing yet definitive here in Europe. There is only a provisional code, which, well, it's not even available for designers. So what have we done? In order to know what kind of heat we should use, we use here what I'm showing you here. This is the quite old 75, a quite old interior fire curve. So basically, we pick up what the fire curves which were used to be for the design of other type of structures, like basically steel structures. This is used in steel structures, and we adopt those curves for the action on our beam. This is called the interior fire curve. There is also an exterior one, which is actually less demanding for exterior design of structures in the exterior. So there's no specifics, let's say, solicitations yet to FRP structures. Now, what we know is that these kind of structures, I wouldn't say they suffer more, because steel structures are also, they have to be protected according to any standard, okay? Usually we do some coating over it with some element that can sustain fire during a period of time. Basically, is this. And so concrete structures, they perform better to fire due to the quantity of air that is enclosed in the concrete. For GFRPs, we are still studying, okay, but we just pick up what we had from other type of structures which also suffers from fire as are the steel structures. But for steel structures, everything is already very well studied, and we know exactly how to design. In fact, for steel structures, it's written in the codes what do you have to do to guarantee that for at least a certain amount of time you won't have problems. That's it.
So more questions? Luis, please.
Thank you. Well, first of all, thank you very much for your talk, Carlos. I was wondering, I'm sure you are aware of the work of Gennaro Camochin regarding GBT, generalized beam theory. And I was wondering if you have any thoughts on the application, since you're in the thin-walled world, if you have any thoughts on the application of GBT with GF or P, and if you have any thoughts, how do you think research can be developed in that sense?
Well, first of all, Professor Gennaro Camochin is a colleague of mine. He has office in the same floor that I have. Mm-hmm. He recently retired, and but he's still going once in a while to our department. Well, GBT, it's a bit different from what we are doing. I would say from what we are doing it's a bit more general than what you have in GBT, in the sense that I'm using this for beams, but if I would have any other structure, I still could use my shell theory. On the other way, GBT saves a lot of degrees of freedom in relation to what I'm doing, because in the end you still have like a condensed degrees of freedom to an axis. Okay, I lost the notion of the axis with the shell that I'm using. As far as I know, but I'm not absolutely sure, they never use GBT like for this kind of analysis. But I would say that you could go, what I'm doing in here, you could also achieve that with GBT. My main concern in that is that I never saw like using the GBT for geometrically exact. Geometrically exact in the sense that you can have arbitrary displacements. But I must add that for what we are specifically doing, I also don't expect to have displacements that justify such theory, such a sophisticated theory. Okay. Also, in GBT, as far as I know, they, or at least they are not using full 3D constitutive equations. Okay, I think they are using a kind of reduced. Well, in the end, is a plane strain assumption. I think. Okay. I must say that I saw the development of the GBT in my department, but well, if 15 years ago it was relatively easy to be aware of everything that they did on GBT, today there is so much work that it's difficult to keep up with everything. Okay. The GBT, if you use the GBT for this, that I must say it would be possible. You still have that problem that I have here of transmitting the information from let's say the real cross section to our theory, no matter what cross section, like this detail. Okay, I think you can see my mouse. In GBT, you still have these kind of problems. Okay, so in the end, there is still this I would say disadvantage of having to transmit something from a real cross section to something that we are considering, because in GBT you also have a thickness variation along a thin mold. Okay, but I think yes, we could use it, and I wouldn't find, at least in principle, I wouldn't find any limitations. We would have to see the constitutive equation, but probably it would be possible as well to incorporate something like I did, which is you just have to express how add some degrees of freedom to the thickness variation. As long as you assume the cross section doesn't have to be rigid, and it can change in plane and out of plane, I think you can accommodate a full 3D constitutive equation. Okay.
Thank you. I'm sure that Professor Dinar will have a very heated conversation with you if you bring the topic. Like he's always defending GBT, of course. But I would be very interested to see some comparisons. I think it's actually something that, as you said, it is possible, but we have to discover what are the limitations once we are actually applying it, right? But thanks.
Carlos, Ronaldo Chaves is asking you if this modeling approach can be used to space propulsion, for example, to the design of the rocket motor case. What do you think?
Well, it's very far. I must say that it's very far from my field, so I wouldn't know how to answer, because I'm not sure what is the exact problem. So here I'm just thinking in a beam heated from the bottom and studying its behavior. On the part of the shell, let's say, if we forget that we are talking here about a beam, in fact, I can use this for any surface heated on one face, let's say, and make the analysis. Well, I can have the surface, and I can have arbitrary number of cells, and then other surface. You can have curvature, and in fact, of course, when we developed and implemented this shell theory, of course, we did all the benchmark tests on shells. And well, here we are just using for a very particular case, which is a cross section extruded along an axis. This is, and here, even here, the axis is straight. But of course, we did all the tests in, you know, those benchmark tests where you have a can of beer and you put two loads and pinch it, and the hemispherical, cylindrical, and so on. So the theory, what I think in here that we can pick up from here and put in other examples that have heat and very thin walled structures, would be the ingredients of the shell theory and also the ingredient of the three-dimensional constitutive law. Okay, here I must say that we regarding to the constitutive equation, we don't exactly develop new things. So we have a potential, we have part of a potential for including fibers, okay, and the temperature was already there, the viscous part was already there, okay? So I think the main thing that we could pick up from here and try to go to other parts, okay, other simulations would be the geometrically exact shell theory, which can incorporate full 3D laws, including, of course, the effect of the temperature. So, regarding to this very specific model where I'm using the thermal part and transferring to the shell, well, that would really depend critically on the shape of what I'm modeling. Don't forget here, and this is crucial, don't forget here that I'm assuming that this distribution of temperatures does not vary significantly along the span of the beam. If I lose like a beam like domain of analysis, then I cannot apply this part of the there is here a figure which explains a bit this figure, okay? So if I don't have something which is similar to this set up with a constant cross section, I cannot use my model, okay? I didn't spoke about this. So the oven goes from one support to the other. So this part goes from one support to the other. I think now you can see my mouse. From here to here, there's no heat underneath. So what we do is just a linear interpolation in between these edges. And we say we have air temperature in the end, and we have the oven temperature in this cross section. So to be quite concise, I think the part of the shell and the 3D constitutive relation could be used for a general shell, okay? But then it lacks the thermal part, the thermal analysis, okay? And what we want to avoid in here is a 3D CFD analysis. That cannot be done in a design cabinet, okay, in order to design a structure.
Okay, I have one more question, Carlos, from Fabiano Gonzaga Fumes. He said that the structural model is submitted to a very large range of temperatures. You have more details in the constitutive model, the last viscoplastic model, in order to represent all this range. And how do you identify all the material parameters from the experimental stress strain tests?
Well, that is the most challenging part. That is the bottleneck. Okay, I would say, although let's say the development of the model is not very easy, but at least for us from the computational mechanics is manageable. That part we expected that to be already done. It isn't. It was strongly affected by these times, but that is the bottleneck that we have. So the ISO curve, after 1 hour, we have temperatures around 900 degrees, okay? And this is what is happening in the oven, okay? So if we try to design for that kind of range of temperatures, of course, we not only don't have the data that we need, as it's very difficult to get it. For instance, the oven that I showed a while, so there was an image of a compression test in an oven. Well, that oven, we are doing those compression tests until maximum 250 degrees. Okay, it's this one. So this little oven goes to 250, which is quite far from the 900 that we attain in the bottle. So that part, well, first of all, if you look in the bibliography, it is very, very scarce. Okay, there is for that kind of temperatures, there is no data. Okay, there is really no data. So, of course, what we have to realize also is that after that time, if we look, I think I have an image of temperatures. If you look, not all the cross section is at so this is so this time here is 1 hour, so 3,600 seconds. So this is what the temperatures that we have after 1 hour, and these temperatures they are quite realistic compared with those in the experiments. Okay, so basically, what do we see? We see that we have very high temperatures in the bottom flange, but part of the cross section it has still some properties. Okay, so we see here that this part is not so hot. Okay, why? Because the air is a very good insulation. Okay, and so this is the most challenging part until now. So what we have done is based on the scarce bibliography in the topic, we try to simulate. When we don't have any information on the properties, what have we done? Well, until now, we say there's no stiffness coming from this Gauss point, and that's it. Okay. After a while, so when we don't have any properties, any information, we say disregard the properties of this point. It's like saying the material doesn't exist. Okay, of course, if I continue to do this, what happens? After a while, you don't have equilibrium anymore. So when it doesn't attain convergence, that the beam doesn't sustain the applied loads that we have applied to the system. Okay, so this is a very crude approximation. It's what we've been doing, and it's what we've done in that example that I showed. But that example that I show doesn't go to such high temperatures. But this is the bottleneck. We have a very complicated constitutive model, but feeding it. Something that I have said is that the material, even the material in this profile, is not equal in the flanges and the webs. It's different, it's slightly different. And the properties in tension and compression are different. So, yes, it is a complicated model, and that is the most challenging part, is to make a fit between what we can measure and our model. That is the most challenging part. Although the computational part is not easy, that part, and it's something that we are still studying, and we are performing tests. In fact, those photos of the oven were taken very recently, and even yesterday we went to the lab.
Okay. So I think that's all. Okay, we had very good questions about your talk, Carlos. And again, I'd like to thank you for presenting the talk for us here in this webinar series. And I hope you can come to Brazil to visit us and to take part in the conference. Okay. And I'd like to thank you everyone here to take part in this webinar. And this recording will be available at YouTube soon, and it's available for everyone and for your friends also. Okay, so I believe that's all. Okay, so we can finish this webinar, and thank you again, Carlos.
I would also like to thank you again for inviting me. It was a pleasure. I would like to thank to Professor Lavaki for being so available in helping all the technical problems. And I hope you like the presentation.
Okay.
It was a truly pleasure, and I hope I can come to Mecsol, and all this situation is better, and we can all see each other there.